So welcome everybody. I'm Sotirios Xydis. I'm chairing this session. I'm an assistant professor on computer architecture and embedded systems at Harokopio University of Athens in Greece, and it's my great pleasure to welcome you in session 3 on runtime of HiPEAC 21. This session have some very interesting works to be presented, spanning from monitoring for performance assessment, monitoring for verification, hardware acceleration, memory compression, and security. So a lot of aspects, a lot of interesting aspects. So I'm going forward to the first paper of the session with the title A Black Box Monitoring Approach to Measure Microservices Runtime Performance from Rolando Brondolin. Rolando is a postdoctoral research assistant at DEI, Dipartimento di Elettronica, Informazione and Bioingegneria in Politecnico di Milano, working on the next laboratory, the Laboratory on Novel Emerging Computing Systems and Technologies. He received his PhD from the same institution on last October, and his main interests are related to energy efficiency, scalable autonomic systems, runtime optimizations, cloud computing infrastructures, and FPGA-based cloud management. Rolando, welcome, and
thank you for the introduction.
The stage is yours.
Hi everyone, and welcome to this video presentation. I'm Rolando Brondolin, a research assistant at Politecnico di Milano, and today I will present a black box monitoring approach to measure microservices runtime performance. In the last few years, cloud services became much more structured and variegated with respect to how they were before. In particular, we started with physical hardware and virtual machines, and these resources were baked by cloud providers that serve them on demand, while in the last 5 to 6 years, we saw the rise of Docker containers managed by orchestrators like Kubernetes. On top of containers, developers and system administrators deploy their applications, their user code, and all the things that makes software as a service running. But to make all this software infrastructure work, we have some hidden complexity that is related to the environment, and this is left all to the cloud provider. One of the complexities that the cloud provider has to face is related to power consumption. In particular, that data centers will be accounted for the 8% of the total energy consumption of the world by 2030. And so we need a way to understand how power consumption happens within infrastructures and microservice-based clusters. In particular, because energy budgets and power caps constrain the performance of the system on the one hand. On the other hand, power consumption is also affected by a plethora of different actors, different users, different workloads, and different hardware with the heterogeneity of the hardware. And finally, because the performance are key for production systems, even if workloads generate power consumption. So in the end, we have a trade-off between power consumption and performance. And what we can say is that applications usually provide a service to the user, so performance should be guaranteed. In the end, power savings usually can come from runtime management systems. And to make runtime management system work, we need a way to measure power and performance in microservice-based systems. This is basically what we do. We try to accurately measure latency metrics, performance metrics, and power consumption for each container in a Kubernetes infrastructure. And to do so, we would like to do it with an instrumentation-free approach, so without instrumenting the application code. We want to do it in a lightweight way, so with little overhead with respect to the target workloads and the target systems. We would like to be accurate to observe precisely and in a distributed way the Kubernetes clusters. And finally, we would like to use eBPF so that we can reduce performance issues and reduce kernel module errors whenever possible. To measure correctly latency, performance, and power consumption, we have some ingredients that we can use. And in particular, we need something related to container latency in terms of network activity. We need something related to container execution, resource usage, and power consumption. For what concerns power consumption, we leverage InterRAPL, that provides us power measurements related to the socket, to each socket within a given server. And to attribute power consumption for each container, we use performance counters, and in particular cycles that has a high correlation with respect to CPU power usage. Then to understand when a given container is running within the system, and so to attribute correctly power consumption, we use context switches. So we trace each context switch running in the system so that we can know when a given workload is running or not. And finally, for what concerns container latency, so performance in the networking activity, we use TCP. We instrument the TCP stack with syscall and key probes using eBPF. So to support all these ingredients, we start from, of course, our containers that provides context switches with the Linux complete fair scheduler. Such context switches are then traced by our power performance tracer, which is implemented in eBPF. And each time a context switch happens, we measure performance counters. And all this information are then sent to a user space agent that each second correlates the performance counters data with interrupt measurements. Then we group everything by Docker containers and Kubernetes pod, and then we send everything to a monitor backend that allows us to aggregate further the data. Starting from this basic performance and power attribution mechanism, we added the networking measurement activity. In particular, what we do is define the concept of transaction, which is a set of TCP messages exchanged by a client and a server within the infrastructure. We measure, in this case, the client transaction time, the server transaction time, and the server execution time to process the given request. And this is done, as I said before, tracing the activities running within the TCP stack and the containers in the system. In particular, in this case, what we do is we keep track of all the network connections running in the system. So each, let's say, we understand if we have a client or a server, we record the client IP, the server IP, the ports in the connection. And then we keep track of all the network transactions happening within the system. In particular, we store for each endpoint, for each connection, 240 traces, 240 samples that are then used in the user space to compute the percentiles. So again, in user space, we group for each second by container the transactions, and then we send everything to the backend. Backend that collects data thanks to a REST collector, which is connected to all the agents running in the Kubernetes cluster. Then we have a set of workers that allows to transform the data and segment each metric by host, by pod, and by container. Then we have two microservices that allows to store the data within a time series database. And all the metrics that are stored in the database are then accessed by front-end interface, and then by by two other endpoints that can be used by autonomic tools to provide performance management, power management, and to perform activities related to how microservices connect to each other. In the end, with respect to the metrics that we collect, we have performance counter metrics, in particular cycles, instruction retired, cache references, cache misses, and RAPL core power segmented by container. Then we have performance metrics, and in particular CPU usage and execution time. And then we have network metrics, so bandwidth, number of activities, number of transactions per second, and latency with averages and percentiles. In the end, the data that we collect for the network activity allows us also to build a graph of the microservices so we can understand the distributed dependencies between the various containers within the cluster. We evaluated our proposed solution so that we could try to achieve low overhead and accurate power and performance measurement. We experimented the proposed solution using a small Kubernetes cluster composed by two homogeneous nodes with the cloud level machines. And we used as benchmarks the NAS parallel benchmark for performance counters accuracy and the DeadStar benchmark suite for network accuracy and overall overhead. In particular, we used the social network benchmark and the media microservices benchmark. For what concerns the overhead, we were basically able to outperform current state-of-the-art solutions, both in open source software as well as commercial software. Our solution was able to our solution introduced 4.10% overhead, while WeaveScope, which is open source, introduced 7.42% on average, and SysD Cloud, which is commercial, 6.75% on average. For what concerns the metric accuracy, instead, we go a little bit deeper, and we can see that from what concerns the performance countermeasurements, we were able to stay below 5% more or less on average, where the execution time and the CPU measurements were even lower relative error. For what concerns the network accuracy, in this case, the average values, we can see that for average latency, request count, and byte sent, we were able to stay below 6% on all the benchmarks we performed. For what concerns the network accuracy percentiles, what we can see here is that we were able to stay below 6% again in terms of relative error for most of the cases, other than the read-on timeline, low, mid, and high for the 99th percentile. This is because the network requests that we observed were more than 20 times with respect to the reservoir size that we implemented. So to understand whether we were able to measure the 99 percentiles accurately, we decided to go a little bit deeper with respect to the measurement that we provided. And in particular, we ran again the same experiments, the read-on timeline experiment with different load levels. And here we can see that up to 16 times with respect to the reservoir size, we were able to stay below 3% in terms of relative error on average. So to conclude, we proposed an integrated power and performance monitoring tool for containerized microservices for Docker containers and Kubernetes clusters. We were able to provide an accurate set of measurements with a lightweight approach with respect to the current state of the art. And we achieved that with an instrumentation-free approach. As a future work, we would like to add memory and disk performance measurements and memory-based power attribution. Then we would like to apply attribution-like algorithms to cloud deployments, for instance, to attribute costs within Kubernetes deployments. And then we would like to provide effective and proactive performance advisory based on collected data. Here we provide the link to the repository where you can find the agent code of the overall infrastructure with all the data that we collect and the user interface running within the terminal. So this concludes the presentation. Here you can find our contacts and emails, and again, the link to the repository. Thank you for watching.
Rolando, congratulations for the great work again.
Thank you.
And thank you for the presentation. There is time for one, maybe two questions probably, but I'm not seeing something in the Q&A. So you are very lucky. Your topic is something that I'm working also with some of my students. So I can take the question and we can continue the discussion afterwards. A first question that we have almost in every paper submission is great. You monitor the performance, you monitor the counters, we share the same view on that. But what about application-related metrics like tail latency or end-to-end latency? Can you infer this type of statistics from such low-level data?
Well, yes and no. It's a kind of a particular question. I mean, we are able to measure also all the network activities, TCP and HTTP, when HTTP is not encrypted. So you can basically understand the end-to-end latency starting from a given endpoint, for instance, an Nginx container. You cannot trace the complete request starting from the endpoint at the beginning and all the other containers, but other than well, let's say you're not able to measure the single request going through all the infrastructure. You can have details and data about the overall activity. That is, you have the graph of all the connections and of all the transactions. You cannot jump from one hop to the other, from one container to the other, and follow the request. That's the point. And that's the main drawback of observing these kind of things from the outside. if you're able to instrument the code and if you want to understand at the single request level, so if you want to trace the whole activity, then you need to instrument somehow. And if you need to, you have to.
Okay, yes,
I don't know if
yes,
this answers the question.
I fully agree. Yes, 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 sure, sure. And I don't know if there is, no, I'm not seeing something in Q&A, so allow me to drop another one related to the power measurement. I've seen that you are monitoring the core power. What about the
Yes.
memory power of the nodes? Are you doing something towards this direction to monitor also the consumption related to the memory system?
Well, we are using Interrupl. You're able also to monitor the DRAM power. More or less, it's an estimate as far as I remember. We are trying to correlate some performance counters with the memory measurement, with the energy measurement with respect to memory, so that we can try to attribute also that kind of measurement. But at the moment, we are still with the measurement at the socket level. We're not able yet to attribute the power consumption of the memory.
Great, great. Thank you. So thank you again. I'll personally will follow your work to be sure.
Thank you.
Thank you again, and for the great presentation. And I think that if there are any other questions, probably not. I think we can move on to the next paper. So the next paper is entitled "A Distributed Hardware Monitoring System for Runtime Verification on Multi-Tile MPSoCs." It is presented from Marcel Mettler. Marcel got his master's degree from the Technical University of Munich, and now he is pursuing his PhD under the supervision of Professor Schlichtmann. His research interests lay in runtime monitoring of multi and many core systems in hardware. And I welcome Marcel to start the presentation.
Thank you for the introduction. Welcome everybody, my name is Marcel Mettler and I'm going to introduce our work, a distributed hardware monitoring system for runtime verification on multi-tile MPSoCs. As most of you know, the computational demand of embedded systems keeps increasing, especially in the area of robotics, telecommunication and autonomous driving. This has the effect that also the design complexity in hardware and software keeps increasing, and therefore we need good verification methods. So here I've prepared a small overview of some verification methods. Probably the best known one is testing. Testing scales very well with complex designs, however, it only has a very low failure coverage. On the other axis, we see exhaustive formal verification because it has a very high failure coverage, and to some extent we are even able to prove that our systems work, but they are not very scalable. And a rather new verification method is runtime verification. It significantly scales better than exhaustive formal verification, but also has a significant higher failure coverage than testing. Therefore, we will have a closer look to runtime verification. Runtime verification is basically a two-step process consisting of an instrumentation part and a runtime monitoring part. In the instrumentation part, we add probes to our system in order to generate a trace of data. This trace of data is then forwarded to a runtime monitor, which checks a set of runtime requirements over the trace data and returns a verdict. This is either positive if the requirements are fulfilled or negative if this is not the case. Runtime verification can be used in the pre-deployment phase of the system for testing and debugging, but also in the post-deployment phase for fault recovery, safety, and security. And even though this figure on the slide looks rather simple, the research question maintains how such a runtime verification system could look like on a decentralized system. And if we have a look at the current state of each search, we see that none of the other works fulfill all properties which are required for such a system, because it needs to be scalable, it needs to be configurable at runtime, it needs to be non-intrusive, in situ, and it requires an event ordering mechanism. This event ordering mechanism is especially important because if certain events occur at different places, we need to ensure that the event trace is ordered by the detection order of the events in order to ensure that our conclusions are drawn correctly. And in this work, we have three major contributions, which are one, the distributed monitoring architecture, which consists of a non-intrusive hardware design suitable for pre and post deployment use cases. SortNock, which is a NOC-based tracing interconnect that not only sorts the events, but also distributes them in the complete monitoring architecture, and an ILP-based requirement assignment algorithm, which places the requirements in the individual monitors in order to use the local monitoring resources best. As a matter of time, I will only focus on the SortNock in this talk. In order to understand how the SortNock works, we will first have a look at the overall architecture, which is here illustrated on the right-hand side of the slide. And each component that is drawn in blue corresponds to a monitoring unit. You can see that each CPU is connected to a probe. So thus the probes are able to detect events in the ALU of the CPU, and they forward them via the time monitor to the network adapter of the SortNock. In the SortNock, the events are then sorted and distributed to all monitors in the system. And within the time monitors, we have a logical and a temporal supervision unit, which then checks the runtime requirements. Let's have a more detailed look on how the SortNock is capable to sort and distribute the events. So it consists of a forward and a backward pass. In the forward pass, all events are sent to one target router. This router is marked with the black box on the right-hand side of the slide. And in order to ensure that events from all routers arrive at the same time at the target router, we added a delay buffer at the local input port of each router. And thereby we determine the delay by the diameter of the NOC architecture plus 1 minus the hop delay to the target router. Thus, we can ensure that events that are sent to the local input port of router 0 need the same time to the crossbar of router 3 as an event that is sent to the local input port of router 3. Additionally, we have implemented a timestamp-based arbitration scheme in order to ensure that the events are actually ordered correctly. Now we have a fully ordered event trace in our router 3, but we actually want the event trace in all of our monitors. Therefore, we need to broadcast it in our complete architecture. This you can see by that yellow-green dashed arrow. Here, the event trace is distributed in the complete system, and thus we can ensure that all time monitors have a consistent view on a globally sorted event trace. We evaluated this NOC architecture against a regular NOC architecture with a sorting IP at the local output port. And as it is very difficult to determine the correct depth of the sorting IP in order to ensure that all events are always sorted, we set their parameter. And here the depth depends on an alpha value times the diameter of the NOC. And for different alpha values and the SortNock, we then plotted the hardware overhead on the left-hand and the right-hand side of the slide. On the left-hand side, you see the hardware overhead in terms of lookup tables, and it becomes visible that the sort NOC uses significantly less resources than all other configurations of the regular NOC with the sorting IP. Things look a little bit different for the flip-flops, because here the regular NOC with the sorting IP with an alpha of 0.25 uses slightly less resources than the sort NOC, but here it should be noted that an alpha value of 0.25 is already a very low value and probably doesn't satisfy the property that all events are always sorted. So in the end, the overall hardware overhead of the sort NOC is significantly less than in a regular NOC architecture. Besides the hardware overhead, we also evaluated the network latency, and therefore we injected 10,000 random trace elements for different event per cycle per system ratios. On the bottom of the slide, you see two plots for an event per cycle per system ratio of 0.1, which is in the area of runtime verification already a very high value. And on the x-axis on both plots, we see different sizes of the NOC design, and on the y-axis of the left plot, we see the latency. And from this plot, we can see that the sort NOC significantly scales better for large architectures than the regular NOC with the sorting IP. On the right-hand side, we plotted the latency histogram for a 6x6 NOC architecture and an EP-CPS of 0.1. And from here, it can be seen that almost all packets have a lower latency from the sort NOC than from the regular NOC. You might be wondering why we have so much more packets in the sort NOC than the regular NOC. This simply comes from the fact that the sort NOC broadcasts all events to all tiles. This is not the case for a regular NOC architecture. So this can be seen as an additional benefit. Yes, and with that, I already come to the conclusion. We propose a distributed monitoring architecture that supports temporal and logical supervision, which can be used pre and post deployment for runtime verification. And the key of this monitoring architecture is the sort NOC, which is a scalable tracing interconnect that inherently sorts and distributes events, and it also outperforms a regular NOC architecture with the sorting IP in terms of area and latency. Here you can see my sources, and this already concludes my talk. I'm happy to answer your questions at the HiPEAC conference. Thanks.
Thank you, Marcel, for your presentation. Very interesting work. There is a question for Marcel from the audience, from Albin. Albin, you can pose your question in the chat, and I will transfer it to Marcel if you want.
I was thinking I could take it here because I have, because I have a microphone. You mentioned that there is a much larger number of packets generated by the sort NOC compared to a regular NOC with a sorting IP. Is there a risk associated with this, that the NOC may get saturated, and does that have performance implications?
I would say that first of all, it's more like a feature, because the initial target is to distribute events in the whole architecture. And with the system, with the sort NOC, you have the ability that if one event occurs, all monitors in the system get informed about the event. However, if you would use the regular NOC, then you would need to send a packet to each interested monitor separately. So first of all, I would say that the regular NOC does not satisfy the requirement which we have at that point. But I would also agree with you that the performance or the throughput of the sort NOC is limited by that. because with that we are only limited or limited by one event in the whole system per cycle. But this is typically not a problem in the area of runtime verification, because there the event density is rather low. So you wouldn't expect an event every cycle. It's a very unlikely case.
Thank you.
So thank you, Marcel. Maybe in the same spirit, is this the short knock requires something like a global synchronizer? So can it support, for example, to have cores with different frequencies, running in different frequencies, or you need something more to enforce the checking, the correct checking, the order checking?
That still would be possible, because each tile has its own, so to say, timer that is synchronized with all others, and then by the timestamp you have, then you can still sort the events. The only thing that would need to be changed in order to support multiple clock domains in the design is that the FIFO at the input port of the router is a cross clock domain FIFO. But this is something you would anyways need for each interconnect.
I see. Great. So thank you, Marcel, again for your work and your presentation. And I think that we should now go towards the third paper for the third presentation by Dennis Pinto. The paper is entitled Design and Evaluation of an Ultra-Low Power Human Quality Speech Recognition System. Dennis will present the paper. He has his bachelor degree from in computer engineering from University of Madrid, and his master degree in robotics and automation from Carlos III University of Madrid. He joined the Arco research group at Polytechnic University of Catalonia on April 2018, and he's currently pursuing his PhD. While his research focuses on the area of hardware support for automatic speech recognition. So, Dennis, the floor is yours.
Hello and welcome to my presentation. I'm Dennis Pinto, main author of the work I'm presenting. In this work, we propose an heterogeneous architecture for low-power, high-performance speech decoding. But why low-power speech decoding? First, let me start by defining word error rate. Word error rate is the most commonly used metric to measure the performance of speech decoders. It's computed by taking the number of substitutions, which are words that are misdecoded, number of deletions, which are words that appear in the reference but are not part of the transcription, and the number of insertions, which are words that appear in the transcription but were not part of the original reference. We add them together and divide them by the number of words in the reference, meaning that word error rate is the relative number of errors by word. If we look at the decoders proposed over the last few years, we see an impressive reduction in word error rate. These results make possible the range of real-life applications that we have seen materialize many times, usually as cloud services or devices. Given this trend and the great potential of a reliable speech decoder to change how people interact with technology, we believe that eventually speech technology will occupy a central role in human-machine interaction. However, one of the current challenges for mainstream implementation is that the kind of devices that will take the most advantage of this technology are usually small, run on low power, and depend on batteries. But speech decoding is computationally expensive and energy hungry. And as a consequence, the most popular current approach relies on external servers, which we think is a less than ideal solution because of several well-known concerns, such as privacy and unreliability of communications. In this work, we provide an analysis to support the idea that the speech decoding can be performed locally on low-power devices by including specialized hardware accelerators. This solution allows for fast and low-energy decoding with a very small area overhead and no reduction in accuracy. So, which components of the decoder should be accelerated? To answer that, we decoded a set of utterances with a representative speech decoder on a CPU and a CPU-GPU low-power architectures, and looked at the execution time. In this plot, the 3 bars on each architecture each represent an utterance on a different percentile of real-time factor. The first one is a fast utterance, the second one a median utterance, and then the last one is a slow decoded utterance. The different colors represent the components of the speech decoder. First, we have MFCC and iVector, which are part of the process to transform the input signal into a sequence of frames. Then we have Viterbi, which is a beam search over the decoding graph, and then TDNN and RNN, which are the neural networks included in the process. TDNN is used for acoustic classification, whereas RNN is used for language modeling. So when we look at the utterances evaluated on the CPU architecture, it is clear that the TDNN and the RNN are the bottlenecks in execution time. When these components are accelerated on the low-power GPU, as we see in the CPU-GPU architecture, then the Viterbi beam search acquires relevance. Based on that, we propose the inclusion of 2 low-footprint components on the CPU-based architecture: a DNN accelerator and a beam search accelerator. First, the DNN accelerator. It is based on a DNN architecture. It contains some internal memories to store weights, inputs, and outputs, and a compute unit. This unit is divided in a set of slices that operate in parallel, each of which is a segmented multiply accumulate vector unit. The beam search accelerator performs the beam search over the decoding graph, which is a data-intensive algorithm with an irregular memory access pattern. It contains several caches and a hash memory, along with different components to fetch data and compute the weights of the visited paths in the graph, according to the Viterbi algorithm. In the platform we propose, these accelerators are included along with a low-power CPU. In this platform, the 2 accelerators perform the most compute-intensive components of the decoder, whereas the CPU is relegated to the direction of the operation of the decoders and the operations that are not well suited for them. For a general decoder, the decoding process goes like this. First, the signal is transformed into audio frames, employing the CPU and the DNN accelerator. In this process, the MFCC and the iVectors are computed, meaning that there are no neural networks involved here. However, the many matrix multiplications operations that are required to perform this transformation are efficiently handled by the DNN accelerator. After that, the frames are fed into the acoustic neural network for acoustic unit classification. This process is entirely computed on the DNN accelerator. These acoustic units, which are represented as probability distributions over the complete set of acoustic units, are read by the beam search accelerator and composed, along with lexical and language information, into a decoding graph. Finally, the language information in the graph can be rescored optionally by a language neural network in order to improve accuracy, and then the final transcription can be extracted. So let's look at some numbers. In this figure, we plotted the cumulative frequency of real-time factor for the utterances on the test set. And we did that for the three platforms, the CPU with a low power GPU, and CPU with the accelerators. When a test set is decoded on the CPU-only platform, most of the utterances run much slower than real time. When they are decoded on the CPU-GPU platform, in which the neural networks and other matrix multiplications are accelerated on the GPU, the overall execution time is improved. However, there are still many utterances that run slower than real time. When a test set is decoded on our proposed platform, the real-time factor improves by a significant amount, while allowing all the utterances to run much faster than real time. Regarding power dissipation, this platform runs at 1 watt, with a peak of 2.5 watts during the iVector computation, which is when the CPU is doing intensive work. Another thing to note here is that the LPDDR memory is the main power bottleneck. As a consequence of that, the memory is responsible for the major part of the energy consumption, accounting for 71% of the total energy. It is followed by the CPU, that accounts for 26.6% of the total energy consumed. In this platform, the accelerators account only for a marginal part of the energy consumption, with 2.25%. To summarize, in this work, we have shown that the current SOCs are augmented with a DNN and a beam search accelerators, utterances can reliably be decoded much faster than with current low-power architectures, with important energy savings and conserving baseline decoding accuracy. Given that the chip area overhead of this solution is negligible, in overall, a solution of this kind is a very good candidate for actual implementation in small, low-power, battery-dependent devices. Thank you all for your interest in our work. If you enjoyed the presentation, please stay for the Q&A session, where I will gladly answer your questions and comments. And don't hesitate to check our paper if you want to know more details about our work. Bye.
Thank you, Dennis, for your presentation. Very accurate, very concrete. There is a question from Rolando. If it's okay, I can pose the question. He asks, which kind of platforms do you use for the evaluation for the numbers that you presented? Your microphone is muted, probably. Now it should be okay. No. You can answer in the chat. I think it's okay. So yes, so the evaluation has been performed on a set of different tools. So it was for GPU, it was the Jetson TX1 board, so a low power one. And for the accelerator was an ARM low power system on a chip. So the accelerators has been on FPGA or has been modeled through EDA tools. Okay, yes. So the models has been either analytical models or used simulators. Dennis said, great, thank you.
Thank you.
My question would be if Dennis, you are interested in exploring low power techniques for the memory side, because I've seen that you had around 70% consumption on that for the power. I guess that the answer would be yes, which give me a point to move to the. Thank you, Dennis, for the presentation again. So, which give me the point to go to the next presentation on the MemSZ, the squeezing memory traffic with lossy compression from Albin Eldstål-Ahrens. Albin is a PhD student at the Computer Science and Engineering Department of Chalmers University of Technology at Göteborg in Sweden. He works on approximate computing techniques, trying to apply this type of techniques on the general problem of memory bandwidth limitations. So I think it fits perfectly with the last presentation. So Albin, the stage is yours.
Thank you. Hello, everyone, and thank you for coming. My name is Albin. I'm from Chalmers University of Technology in beautiful Gothenburg, Sweden, and I'm here to present our article entitled MemSZ, Squeezing Memory Traffic with Lossy Compression. In the common memory hierarchy, there's a stark difference in performance between on-chip elements, such as caches, and off-chip elements, main memory and persistent storage. One cause of this is the main memory bus, which can become a bottleneck due to its limited bandwidth. This graph shows the performance of a system with an ideal infinite bandwidth memory bus. 1.0 in the figure corresponds to a system with a realistic bus. Now, among these benchmarks, performance could be improved by an average of 45% if the bandwidth bottleneck was removed. Likewise, total system energy could be improved by an average of 21%. Our approach to this is to reduce the traffic on the bus using compression. By compressing data before it hits the bus, the bandwidth pressure can be relieved, and this allows greater performance and reduced energy consumption. Two key observations help us maximize the impact of compression. First, some applications are able to tolerate small approximations in their data, and this can be exploited to apply more aggressive lossy compression methods. Finally, in order to increase the achieved compression ratio, we aim to compress blocks 16 times larger than the typically transferred cache line. Now, this approach poses two major challenges. First, by exploiting approximation, we risk introducing excessive error in computation. Any system like this must have a mechanism to control the introduced error and limit its impact on the executed program. Second, the performance of decompression is crucial since the memory reads are on the critical path. Decompression must be faster than the 100 or so cycles of a fast memory access. This paper takes its basis in approximate value reconstruction. AVR provides an architecture for lossy memory compression, as well as an LLC design able to store both compressed and uncompressed data. We extend AVR with a design we've dubbed Memory Squeeze, or MemSZ. Its contributions are, in order, a specialized hardware implementation of a more advanced compression algorithm known as Squeeze, or SZ, a new replacement policy which allows for better utilization of last level cache space, an additional global error limiting mechanism, and finally, an additional architecture which combines lossy memory compression with a 3D stacked DRAM cache. Now let's look at each of these contributions in order. Squeeze is a lossy compression method which works on sequences of numbers. And the idea is to describe each number not as a value, but as a function of the preceding values. With a limited number of fixed functions to choose from, there are a limited number of options, and therefore less information to store. The squeeze algorithm to compress a sequence of values is as follows. First, decide how lossy you want your compression to be. Then, pick some starting values, we call them seeds. These are the first few values in your sequence. Then, for each value that follows, try 3 different fixed functions, and if any of them is close enough, use a 2-bit symbol to indicate which function worked the best. If not, the value is an outlier and must be stored. When this is done, we've compressed our sequence of values, and all we need in order to decompress them is the seeds, the 2-bit symbols, as well as any outlier values that we've identified. Now that we know how squeeze works, let's look at how suitable it is for memory compression. Recall that to be useful, our decompression must be able to compete with a 100-cycle memory read. Squeeze has some drawbacks here. First, as we just saw, it is entirely sequential. The latency of decompression is proportional to the length of the sequence that we're decompressing. Second, the complexity of the individual functions it offers is too great for single-cycle computation. Our first contribution, therefore, is the adaptation of squeeze to be suitable for memory compression. First, we've employed several pipelining optimizations to ensure that one value can be processed every cycle. Data flow techniques allow parts of decompression to be performed out of order, and most importantly, we've broken the sequential processing of standard squeeze by reorganizing the data in a 2-dimensional block and starting multiple squeeze sequences in parallel. This is the key to better performance. Allow me to demonstrate it. First, we take our 16 cache lines and we arrange them in a square, like so. Then we select our seeds or starting values. We choose the 4 values right in the center of the block. Now from each pair of seeds, we can start processing both up and down in parallel, giving us these 4 struts running vertically down the middle of the block. From there, we can parallelize even further. Once the struts are ready, we can start 32 parallel arms spreading out towards the edges of the blocks. Normal squeeze would have had to process all of these values linearly. With our technique, the critical path is 1 strut of 7 and 1 arm of 7. So we've reduced the complexity to the square root of n. The second contribution increases efficiency in the last level cache. As you may recall, AVR stores both uncompressed cache lines, like A1 here, and the full compressed blocks that they belong to in the LLC at the same time. There's data redundancy here, amounting to LLC pollution. MemSqueeze attacks the problem using a different replacement policy. When we have both, compressed blocks are prioritized over duplicate uncompressed lines, and this way, when it comes time to replace data in the cache, it's more likely that an uncompressed line gets replaced than the compressed block. Third contribution is a more robust error limiting strategy. This is a histogram over the total accumulated error per block over the entire execution of an application. Now, as you can see, the vast majority of blocks end up near 0, meaning they've accumulated only a small error over the entire execution. There is, however, a long tail of blocks with higher accumulated errors. These blocks may cause disproportionate effects in the quality of the output, and it's therefore a valuable trade-off to disable compression for these specific blocks if we can identify them during runtime. MemSqueeze maintains an accumulating error counter for each individual block and permanently disables compression past a certain threshold. This has the effect of cutting that long tail of sensitive blocks. The fourth and final contribution is an alternative architecture for systems equipped with 3D stacked DRAM caches. Now, MemSqueeze with a DRAM last level cache is a natural extension to the system we've seen so far, except no compressed data is stored on chip. By employing a suitable line size in the DRAM cache, full blocks fit perfectly. This simplifies large parts of AVR's cache design. Finally, let's talk about the impact of MemSqueeze on system performance. We've implemented the design in a processor simulator and chosen benchmarks which tolerate some amount of approximation. We then annotated data structures in those benchmarks and applied lossy compression to them. We compare our design to 3 competing approximate computing techniques. First is Doppelgänger, which is an approximate deduplicating last level cache. The second is Truncate, which implements a simple 2-to-1 precision reduction in both main memory and in the last level cache. This reduces traffic and increases the capacity of the LLC. Finally, we evaluate the current state of the art, AVR. And we'll look at results of these simulations in terms of 4 key metrics: memory traffic, performance, energy consumption, and output quality. First, memory traffic. The purpose of memory compression is to relieve the pressure on the main memory bus. On average, MemSqueeze reduces memory traffic by 54%. Second, raw performance. The reduced memory traffic has a greater effect the more memory bounded an application is, and we see improvements ranging from a few percent all the way up to 60%. On average, MemSqueeze gives a 36% reduction in execution time. Third, total system energy consumption. This is improved by the reduced execution time that we just saw, as well as reduced activity in main memory. MemSqueeze manages a 13% reduction, making it the most successful design. Finally, since these are approximating systems, we look at the output quality of each benchmark. This is done by comparing the generated output to that of the baseline system. We find that for the majority of our tested applications, the output error remains below 2%. MemSqueeze manages an average of 0.9% output error. In conclusion, MemSqueeze is an approximate memory compression scheme which surpasses the previous state-of-the-art, AVR, in terms of traffic, performance, and energy reduction. With that, I thank you very much for listening, and I look forward to the discussion. Thank you.
Thank you. Thank you, Albin. Very, very interesting work. Very interesting work, indeed. I don't know if there are any questions from the audience. No. So I can. I have a question actually. You've said that at the end, the data that you are storing on the on-chip caches are not compressed, right?
No, they are. We store both uncompressed and compressed data in the last level cache.
Okay. So have you faced any problems with cache coherence between parallel applications and stuff like that when the data are compressed?
No, we don't tackle this problem because we apply this to a shared last level cache, which is shared between all of the cores in the system. So coherence doesn't really come up.
So there is no possibility for one processor to change a part of the compressed data and then have to update the shared object.
No.
Okay. Okay. Great. Great. And are you considering to cooperate the approximation on the data with approximation of the actual data path, so to have a full energy efficient approach? Because now you approximate your memory structure, but there are also many techniques for approximation on the actual computational part.
No, we haven't looked into combining these two, and in some sense that's an interesting problem on its own because the errors that you introduce would compound, right? If we introduce some error in the data while we're transferring it from memory, and then the data path, say an approximate addition instruction, is able to or introduces some additional error, then these they will accumulate, and this is something you have to be rather careful with, because the output quality of the application, of course, is important. We haven't, but it's an interesting idea for future work, definitely.
Great. Very interesting work. I'm really impressed. So thank you again, Albin.
Thank you.
And we can move to the last presentation of the session, the SGXL security and performance for enclaves using large pages. The presenter is Sujay Yadalam. Sujay is a PhD student at the University of Wisconsin-Madison. His interest lies on computer architecture and systems. And in the past, he has worked on hardware security, while currently his main research interest is on memory systems. So, Sujay, welcome, and we're happy to follow your presentation.
Hi, thank you for coming to my talk. I'm Sujay Yadalam, and I'm happy to present our work on hardware security pertaining to side channels in the Intel SGX, which we dub SGXL. This work was carried out under the guidance of Professor Vinod Ganapathy and Professor Arkaprava Basu at the Indian Institute of Science. In this talk, I'll be going over the basics of Intel SGX. We will then look at an interesting vulnerability called the control channel attack. I will talk about our work SGXL, which defends against the above mentioned side channel. And lastly, I'll present some results from our experiments. Now, cloud computing has gotten ubiquitous in the past decade. The problem of secure remote computation has never been more relevant. In the cloud setting, clients execute software on a remote computer that is owned and maintained by an untrusted party. Often, clients share the resources with other users of the cloud. Intel SGX aims to protect the confidentiality and integrity of the user's code and data from other users of the cloud and the untrusted cloud provider. It does so by planting its root of trust in the hardware. Now, past research has shown that a malicious actor can leverage this system software to compromise the secrets within a victim process. In the cloud, the hypervisor is owned by the untrusted cloud provider. Hence, the SGX model excludes the operating system and the hypervisor from the trusted computing base. By including only the hardware in the TCB, SGX is able to defend against strong adversaries, including a malicious operating system. Now, before we dive into the details of our work, I would like to quickly introduce you to some of the key terminologies relevant. SGX applications define a private range of the address space called enclave, which hosts the secret code and data. The enclave contents are loaded into a reserved region of physical memory called the enclave page cache, or the EPC. The hardware protects the contents of the EPC by encrypting the data and monitoring accesses to it. It prevents any unauthorized user from spying on or modifying the contents of the EPC by maintaining some necessary metadata in a hardware structure called the EPCM. The EPCM includes information such as the page owner, the linear address offset, and permissions. One of the key design aspects of SGX is its reliance on the operating system. SGX delegates the task of the EPC page management to the untrusted operating system. As you can see from the figure, the page tables of the enclave process still reside in the insecure region of system memory. Now, this reliance on the untrusted operating system opens up a side channel through which a malicious user can monitor the page accesses being performed by an enclave application. An adversarial operating system can modify the page tables and induce page faults. A smarter attacker could just monitor the accessed and dirty bits in the page tables. An unauthorized user can launch a timing side channel attack against the TLB to capture the page access tree. Now, at this point, you may wonder what an adversary could achieve by learning the page access pattern. Interestingly, researchers found that page access pattern can be used to learn about secrets being processed by an application. Let's look at an example. HUnspell is a spell checker library that stores all the words using hashing. It uses a hash table and linked list to resolve aliasing. Now, these structures can span multiple pages as shown in the figure. Now, to check the spelling of an input, the program traverses the linked lists to find a match. Now let's assume that an adversary is monitoring the page accesses of this application. Let's say that he sees an access to page 1 and then an access to page 5 and then an access to page 6. Now, if this adversary is aware of the data layout, then he could easily infer that the word being spell checked was channel. A similar attack was demonstrated against the libjpeg library. When images were being decompressed by this library, an adversary was able to recover the images as shown. Now, there have been several proposals that try to defend against these attacks, but all of them fall short. They either defend against only a subset of the attack vectors, or they require invasive source level modifications. We propose SGXL, which defends against all of the attack vectors and does not require significant source level modifications. Now, the crux of SGXL's design is the use of large pages. Typically, applications use the default page size of 4 kilobytes to map virtual addresses to physical addresses in x86 processors. Modern processors allow system software the choice of mapping memory at a larger granularity of 2 megabytes or 1 gigabytes, called large pages. Now, typically, large pages have been used for better performance. Here, we argue that they can also be used to defeat page address-based attacks. Let's look at an example to understand how large pages aid in defending against page address-based side channels. Earlier, we saw how an attacker was able to guess secrets based on page accesses. Now, with large pages, on the other hand, all of the data would reside on a single page, here page 1. If an adversary is trying to monitor accesses to this page, he can only observe a single access to page 1. He can no longer guess the secret based on this information. In this way, large pages significantly lower the resolution of the leaked address stream. And from our experiments, we observed that this is typically enough to defeat any known incarnation of the page address-based attacks, as an attacker is left with very little information. However, using large pages is not sufficient, as there is an underlying problem. Similar to SGX, SGXL relies on the untrusted operating system to manage the EPC pages. A malicious operating system could therefore not provide the enclave with large pages as requested. Therefore, SGXL needs to ensure that enclaves receive the required page sizes. Now, we break this into two subproblems. We propose minor hardware modifications to address each of this. To ensure that large pages are provided to the enclave when it is created, we make changes to the enclave measurement process in SGX. In SGX, before an enclave begins execution, the hardware ensures that the enclave was created as required and a malicious operating system has not meddled with its contents. And now the hardware does so by computing the hash of the contents of the EPC and the offset at which it is loaded. This hash is then compared to a hash that is calculated on the client side by emulating the same process. In SGXL, we add the page size to the hash measurement. This will ensure that an operating system provides the right page sizes to the enclave application as requested. Now, the second subproblem is to make sure that the operating system does not modify the page mappings during enclave execution. To this end, we make changes to the access checks performed in SGX. In traditional systems, memory is accessed once the virtual address is translated to physical address. In SGX, after the virtual address is translated, additional checks are performed to ensure that an authorized entity is accessing the data within the EPC. Now, it does so by consulting the metadata that is stored in the EPCM. In SGXL, the EPCM holds the page sizes along with the other necessary information. Now, this page size that is stored in the EPCM is cross-verified against the page size that is obtained when the address translation is performed. For more details on how SGXL supports large pages within an enclave, kindly read our paper. Now let's look at some results. We studied the effectiveness of SGXL by measuring the number of unique sequences that an adversary could observe. We used the term bigram to define a pair of page addresses that could occur in the page address stream. As can be seen from the table, SGXL significantly reduces the number of sequences that an attacker can observe. This means that an attacker is left with very little information. We thought that this reduction was sufficient to prevent an attacker from learning the secret being processed within the enclave. Moving on to the performance, large pages reduce the address translation overheads, thereby improving performance. We observed similar results. SGXL performed better than its counterpart, which uses the default page size of 4 kilobytes. Now, SGXL is one of those rare systems that enhances security while also improving the overall performance. To summarize, SGX is susceptible to page address-based side channel attacks. We proposed a defense called SGXL, which uses large pages to defend against these attacks. Large pages reduces the granularity of the page address stream. SGXL includes minor hardware modifications to guarantee the use of large pages. SGXL is unique in that it improves both the security as well as the performance of an application. Thank you. I'll be happy to take any questions at this point.
Thank you, Sujay. Very interesting presentation. And there are two questions also from the audience. There's a question from Rolando asking what is the overhead of the SGXL without considering the benefit of large pages. It is possible to measure such an overhead?
Oh, that's a great question. Can you guys hear me?
Yes, sure.
Oh, great, awesome. So there's basically two overheads of SGXL. The first being the memory overhead, because we're using large pages. And we have indeed quantified the overhead in memory consumption when SGXL is used, and the results are presented in the paper. Most applications that run on SGX are small, and so the memory overhead is not very significant. The second overhead that SGXL introduces is that of the address translation, and we have indeed simulated the access times for SGXL. We see that there is a slight increase in the access times, but the increase in the access times was shadowed by the improvement in performance that occurred because of the usage of large pages. Yeah, that was addressing the first question. Thank you for the question.
Great. And there is also a question from Albin asking that actually what is the, if there is any security loss from applications with large data sets like big data workloads. So I guess he means that at the end you will have to generate sequences towards the TLBs when you have this type of application. So are you considering this type of threats also?
Yeah, this is a wonderful question. So this is actually true. So I think there were two applications that kind of didn't fit within the EPC. There was an application called GUPS, which we evaluated. But yeah, most of the applications that we looked at, could fit in a couple of large pages. And these were applications that, earlier attacks were written on. Now to address the question of large workloads, what we presented was to use SGXL with a compiler technique that was proposed earlier. It was called PAO. And what we showed was that, so the PAO technique works on all workloads, sizes small or big. But what we showed was that when we use SGXL along with PAO, we were able to reduce the number of dummy accesses that the PAO compiler was adding. So in short, SGXL is not able to defend on its own, but it can improve the performance of other existing defenses.
I see. And also a question from my side. For scenarios driven by these cloud-native applications, we have a lot of containers sharing the same node. Are you expecting to see any overhead when you are allocating large pages? So you are starving the memory and not allowing more containers, for example, to co-schedule together?
Again, this is a wonderful question. So we did study that as well. We studied the impact on page contention within the EPC. I couldn't present the results in the slides, but yeah, as you mentioned, large pages would cause more contention. So what we saw was that the major impact was on the page fault latencies. So what happened was that now that you had to, so in SGX model, when you have to evict a page from the EPC, which is a secure region, you have to encrypt it and move it out of that region. And we saw that because we were using large pages, we would have to spend more time. So we saw that the page fault latencies would increase. So to answer your question, yes, if there is a lot of contention on the node, then there would be some impact on the performance. But if there's no contention, then SGXL would perform well.
I see. Great. Thank you, Sujay. Very, very interesting work. Very interesting work.
Yeah. Thank you all for the questions.
So with the presentation of Sujay, we can, I think, close the session. Thank you all for, I will like to thank the presenters, of course, and also the attendees, and with many wishes next year to meet in person with all of you. So bye-bye and stay healthy, right? Thank you all again.